I have created a marble game that runs on this microcontroller board. So when I tilt the board, the marble rolls around on the display like it's on a table. Most of the time it works fine, but sometimes it crashes and just gets stuck like this. Bugs like these are common in embedded systems, and they often start exactly like this. You just get a symptom, and then you have to work your way all the way back to the root cause to fix it. And that's exactly what I'm going to do here. There are a few different ways to start attacking this problem. You can dump and look at the logs, try to reproduce it, or read through the code and make a few guesses. Either way, what you're trying to do is just gather more information about the problem. And for a microcontroller that is stuck or has crashed, the best information is usually inside the microcontroller itself. And one of the main tools we have for extracting that information is a debugger. A piece of hardware that you connect to your chip that lets you control and inspect its execution from your computer. I have a few different ones here on my desk, and they come in different flavors. Which one you use primarily depends on the type of chip you're trying to debug. Though on this development kit, like on many others, there's already a debugger on board, so I don't need to bother with one of these external ones and can just rely on the USB connection I already have. On my computer, to talk to the debug probe, I first of all need a server program, and I'm just gonna pull the one from the vendor in this case. And since I've caught the microcontroller in its crashed state and I basically want to do an autopsy of it, I want to make sure that when I connect to it that I don't reset it. So now I'm connected to the debug probe, and the second part I need is the front end, which is typically gonna be GDB, and I point that to my compiled program and connect it to the server I started in the other terminal. I'm using the debugger from the command line first because it makes it easier to see how the pieces fit together. Later I'm going to use the debug interface in VS Code instead. Now, to use a debugger effectively, you need to first of all understand what you're looking at. So let's do a quick recap of that. We have registers and memory. The registers are a small set of values that the CPU works with directly, its own workspace essentially, while the memory is the big storage next to it. RAM for the program's data and flash for the program itself, and they contain everything we can learn about the current state of the chip. It makes sense to start with the registers because they tell us what the CPU is up to right now. There are many registers, but a good starting point is the program counter register, because it holds the address to the instruction the CPU is currently executing. And if we are stuck, that should tell us where in the program we are stuck. But then we must also find the instruction or program line this 32-bit value corresponds to. And there are multiple ways we can do that. One crude way to do it is to look at the program file that was flashed to the microcontroller and scroll through it until you find the address. But a more practical way to do the same lookup is to just use the debugger instead. It's in a default handler inside the startup file. So this is where the microcontroller is stuck inside this infinite loop. Now a function inside this startup file or a handler like this is something that the CPU jumps to on its own when something specific happens, like an error or a hardware event. And if you want to do something specific when they happen, you can define a function inside your program. But if you don't do that, usually there is going to be a catch-all default handler that they point to instead, which is exactly what this default handler is. So right away, this at least places us somewhere inside the program, the first useful piece of information. But there is some confusing output here as well. The debugger says watchdog handler here, and the object dump said ADC handler. And that's because they can't really say which one it is, because as I said, there are multiple symbols or exceptions pointing to the same default handler. And they are arbitrarily just showing one of them. And this is a good point to bear in mind. Sometimes the tools mislead you, so you have to be on your watch when you're using their output to understand what's going on. What this means for us is that we don't know which exception got us here. For that, we need to look at some other registers. Exactly which ones that are going to be available at this point will depend on the particular architecture, but some form of status registers are common. On a modern architecture, they can tell us quite a lot. On ARM Cortex-M, the main one is the program status register, which is part of the CPU core. You can decode this value by hand and then look into the datasheet to see what it means, or nowadays just drop it into your language model of choice. But at this point, though, I will switch over to VS Code for the rest. It's the same GDB underneath, just nicer to look at. And to do that, I need to install an extension, Cortex Debug. And then I also need a file describing my debug setup. And then attach, and we end up in the same place as before. And then I can look at the registers in the side menu, and here is the same register. And if I hover that, it decodes the numbers for me. And here it's telling us it's the exception or interrupt number 3 that has triggered. And referring to the datasheet, that corresponds to a hard fault, which is serious because it means the chip tried to do something illegal. But the good thing is that it throws this exception the moment the illegal operation happens. So now we got a crime scene to look at. Moreover, since it is a hard fault, we can also look at hard fault status register for more information. But that register doesn't live among these other core registers. Instead, it's part of the system control block registers. And those are memory mapped, so we can read them like we read any other memory. But to avoid having to read them manually in the memory view, one helpful thing you can do with your debugger is to also add a system view description file, which is essentially an XML file that describes these registers so that the debugger can parse them. This is the hard fault status register, and here one of the bits are set, the forced bit. This helps parsing, but you still need to go to the datasheet to understand what it means. And the forced bit means that another more specific fault happened, but it got escalated into hard fault instead, because by default the exception handler is not enabled for each fault type. But even though they don't trigger a separate exception, the type of exception is still recorded, but it's in another register, the configurable fault status register. And inside here we have the imprecise error bit set, which gives us another clue. And this one is particularly interesting. It means an imprecise data bus error, a bus fault, which in practice means that the program tried to write to a bad memory address. Not only that, it's also marked imprecise, because the memory writes are buffered, so the CPU might have continued executing since the write was issued until the exception is thrown, which means we can't trust the stored program counter value to point to the offending write instruction, but we will have to look up the call stack or at the surrounding code. So if we just quickly summarize what we know so far, we know where we are in this infinite loop in the default handler, and that got called when the CPU threw an exception, and the exception was thrown because of a faulty memory write. So we know where we are and why, but we don't know how we got here. And to figure that out, we need to look at the stack, because that's what the program uses to keep track of the execution. And by looking at what's stored inside there, we should be able to reconstruct the chain of function calls that led us to where we are right now. But before we let the debugger do all of that for us, I think it's a good learning exercise to dump the raw contents of the stack and roughly decode it by hand first. So the stack is a region inside RAM, and to dump it we will need the top and bottom address. The top one is easy, it's what the stack pointer points to. The bottom one we can either get by looking into the linker script or by knowing that on ARM Cortex the initial value of the stack pointer is loaded from the first address in program memory. So by just looking at the memory at that address we can retrieve it. And the stack grows downwards, so each time a new value is pushed, the stack pointer is first decremented by 4, and then we can use these addresses to get the content of the stack from VS Code. And then I'm just changing the view to grab them into my drawing tool. So these are all of the values stored in the stack currently. To decode this, we need to know what to expect. And the stack is divided into stack frames, typically one per active function call. And each stack frame stores the local data for a function and any registers it has to restore when we return from it. One special case is when an exception happens, because then the ARM CPU always pushes an exception frame to the stack, consisting of 8 specific registers, among others the program counter and the link register, which holds the return address. So that's our first frame. To figure out the frame boundaries for the other frames, we can try to find the frame pointers, because each frame in this case is going to contain a pointer to the previous frame. And a frame pointer is going to be a value within the stack range, so somewhere around hex 20 million. And then we can just assume that the remainder before the exception frame is the last stack frame. Then we can try to find the link register or return address saved in each stack frame, because that's going to allow us to figure out which function each stack frame belongs to. And that's just basically finding the values that looks like program memory addresses. And then we can use the program code and debug information in the ELF file to determine which function an address belongs to. The return address in the exception frame belongs to the function plot pixel, and the program counter to the function count pixel, which then is the function that we were in when the exception happened. Another way to look up these addresses is also just to ask the debugger directly. So draw ball, and function run, and then function main, and lastly the reset handler. And the reset handler doesn't have any stack frame because it's the first code executed, so it has no caller and typically no caller state to preserve. And the rest of the values in between is just the local data or variables. And then each stack frame is going to belong to the function the return address in the next stack frame points to. And there we have it, the entire call stack. Note, count pixel is an odd one because it appears to have no stack frame, but we're gonna understand why in a moment. Now we have the mental model of what the stack contains, but usually you're not going to be hand carving the stack and instead let the debugger do it for you. I should also say that the stack we got here was easier to decode than it normally is, because I built without compiler optimizations. So with GDB we can get the call stack or backtrace with a single command, or simply look at the call stack in the side menu. And with that we see that the exception got thrown in the function count pixel, and the call stack matches up with what we just hand decoded. And looking at the disassembly explains why there is no stack frame for count pixel. The exception was thrown at the very first instruction of this function, so the stack frame hasn't been created yet. And remember, this was an imprecise error, which means we shouldn't expect the problematic instruction to be the one we are sitting at, but rather one a few instructions earlier. Maybe in the function that called count pixel, so we can step up through the... And here we have a likely suspect, a memory write to write a single bit to this frame buffer. The frame buffer stores the image frame shown on the display. The display is 128 by 64 pixels, and each pixel is stored as 1 bit, so in total we have 1024 bytes. And calculating the index based on the function arguments, which we also, by the way, could have retrieved from the stack we decoded earlier, we see that the index falls outside the allowed range. A classic out-of-bounds write. Notice also that it's the page that pushes us over the edge. The display only has 8 pages, so the page number should be below that. But it's not. And to expand a bit, each page stores 128 bytes, where each byte is a 1 by 8 pixel column. Anyway, we have ended up writing to a page that doesn't exist. So we are now narrowing in on our problem. To get further, we need to continue going up the call stack. So what this function does, it's responsible for drawing the ball, which is essentially a round object that is drawn at a specific coordinate, and then it has a fixed radius. In this case, the radius is 4. And here is some code for writing across a page. Anyway, if we once again look at the arguments here, we can see that it was trying to draw this ball at 42 and 60, probably somewhere around there. And that's a totally valid coordinate, but the problem then is that the ball is not just this dot, it's actually larger than that. So we try to write outside the memory, and that we are not allowed to do. So it simply looks like I have forgot to clamp the coordinate values properly. And if we go up another level, we can see here that there we have the problem. I am calculating the new position of the ball, clearing the frame buffer, drawing the border, but then I draw the ball before I clamp the values. Now, looking at this, it seems that it would be very easy to reproduce. It should be enough for me to roll off the edge of the display. But the reason it doesn't always happen is because I'm drawing this border at the edge of the display, and I'm clamping before that. So in order to trigger the bug, I must be going fast enough to blow past the border for this bug to trigger. And also it's primarily a problem when I go off the top or bottom of the buffer, because when I go off the sides, it's mostly going to cause a visual glitch, because then I just write to some other part of the buffer. And full disclosure, I have rigged this setup a bit, because I've placed the frame buffer right at the end of RAM, so that an out of bounds write lands cleanly off the edge and causes a fault. And perhaps the even more interesting case that we have here is when we roll off the top of the display, because then we start corrupting the stack. And that doesn't just break the program in weird ways, it also destroys the very evidence we use to reconstruct what happened. And when you run into these kinds of nasty bugs, then you may actually have to do some hand decoding of the stack yourself. And here you can see we don't get the clean call stack anymore. It's also not going to be as deterministic. It's going to show kind of a different behavior every time it triggers. Here is even warning us, because when the debugger is trying to decode it, it's not able to do it cleanly. And if you just look at what it's showing here, showing 0, and then it's showing an insanely big column value, probably because the stack that got corrupted is the actual argument to this function. So this becomes an even nastier type of bug. The fix for this is easy, but before I fix it, we just had to do a lot of manual work to figure out what happened here. And it would be nice if you could make the chip give us more information immediately next time it happens. And we can do that by adding a dedicated hard fault handler. A common pattern in many embedded stacks is to dump the crash state. And for convenience, I have prepared an example of that. So what this does, it overrides the hard fault handler, so that when a hard fault happens, this one gets called instead. And then I do some manual assembly here as well, to ensure the compiler doesn't insert any instructions that messes up the stack pointer. And here I just print the information over UART. So first the exception frame, and then the fault register, including some annotation. There are more annotation you would do in a complete hard fault, but I'm keeping it simple for demonstration. And then finally I print the stack. And another convenient thing is to trigger a breakpoint in case the debugger is attached. So I can add this to my build. And then reproduce it again, tilting it fast. And now that I know how to trigger it, it's easy to reproduce. And here we get a nicer printout of the hard fault, and we can see that it's a hard fault and that it's an imprecise error. So this is just a convenient thing to have. And to fix it, we can just move the out of bound check to before we draw the ball. And even more defensive would be to put a bound check inside the drawing functions as well. So we just followed the whole chain, from the symptom through what the chip recorded, to the root cause, and fixed it.